Section 12.3 deals with solving geometric problems. So let's just go straight away into example 9. I would always sketch it, even though it's in 3D. You might think, well, how am I going to sketch it? Just give it a go. You can only sketch a 2D representation of the picture that you might have in your mind. So first of all, you don't need to sketch anything to find A, B and DC. But I'll just have a quick look. We're going to show that ABCD is a quadrilateral. Oh, what type of quadrilateral? I guess that's what we are talking about. So I'm going to imagine A, B, C, D, label them in order. So this is 2 minus 5 minus 8. This is 1 minus 7 minus 3. This is 0, 15 minus 10. And this is 2, 19 minus 20. So vector AB. So what do I do to A to get to B? That's going to be 2. I need to take away 1. From minus 5 to minus 7, I go down 2, so it's minus 2. From minus 8 up minus 3, you are going to add 5. Let's just make sure that we got it right. So it's vector OB minus OA. So it's 1 minus 7 minus 3, subtract 2 minus 5 minus 8. 1 take away 2 is minus 1. Minus 7 take away negative 5. So it's minus 7 add 5 is minus 2. Minus 5 take away negative 8 is minus 3 take away negative 8 is minus 3 add 8, which is 5. So there you go. Okay, DC, so from D to C, we are going to go from 2 to 0. We are going down to, from 19 to 15, I'm going down 4. From minus 20 up to minus 10, we're going 10 up. Double check. 0, 15 minus 10, so it's position vector of point C. Take away position vector of point D. So it's going to be 0 take away 2 is minus 2. Minus 15 take away, yeah, that's correct. Minus 10 minus minus 20, it's minus 10. Add 20, which is 10. There you go. So show that the vector AB, which is here, and DC are parallel to each other. So AB is vector minus 1, minus 2, 5. And you could see that if I times that vector by 2, I'll be getting vector minus 2, minus 4, 10. And that is the vector DC. So vector AB when multiplied by 2 is equal to DC. So these are they are parallel to each other. You could say as A vector AB and DC are scalar multiples of each other. Scalar means multiplied by a constant. Okay, we've got to now comment on what type of quadrilateral it is. So you should know, I mean, my diagram was absolutely nothing reflecting that this one is twice as long. But if I draw it the other way around, so it's both A, B, and then DC twice as long, you could see that you're going to get a trapezium. The definition of a trapezium, it has a pair opposite sides that are parallel, not equal to each other. Okay. Question 10 or example 10, you've got PQR being 3 points with the following coordinates, and we have to, given that PQRS is a parallelogram, we need to find S. So let's actually draw the parallelogram. So PQRS So remember the definition of a parallelogram is simply opposite sides are parallel to each other or equal in length. So you don't need to really, just need to satisfy one of the conditions. So either check that they are equal in length, and or you could go show that they are parallel to each other. So you've got two ways of doing it. You don't need to check both. So P is point with the coordinates 4, -9, -3. Q is 7, -7, -7. R is 8, -2, 0. Okay, we're not proving that it's parallel, though. We are looking for the coordinates of that point. It's really, really very simple. You are going to rely on the fact that this vector must be exactly the same as that vector because they are parallel and equal in length. These two vectors also parallel to each other and equal in length. Okay, need to remember that when they refer to parallelogram as PQRS, it goes in the order you name the parallelogram. The points go in that order, PQRS. Okay, so you can't just do PQSR, for example. Okay, so all I'm going to do is use a little bit of common sense. So I'm going to find the vector QR. So QR needs to be found. So it's what do you do to point Q to get to point R. So if you think about it, look at this very carefully. To get from 7 to 8, I add 1. From -7 to -2, I'm going to add 5. From -7 to 0, add 7. And all I'm going to do is add this vector to OP. Okay, let me just check whether I've done the vector QR correctly. So it's 8 -2, 0, subtract 7 -7 -7, and you get 8 take away 7, which is 1, -2 take away -7, -2 add 7, that's 5, 0 take away -7 is 7, so that's correct. And what I'm going to do now, I'm going to find this vector by going to point P, so position vector of point P, add vector QR. So let's just work it out quickly and then we'll write it more formally. So 4 add 1, that's 5, -9 add 5, that's -4, -3 add 7 is 4. There you go, and that's our vector OS, and the coordinates of that point would be 5 -4, 4. Let's just check. So to work out OS, I need to get to point P, so go along OP and add the vector QR because it's exactly the same as PS. Okay, so it's OP is 4 -9 -3, add vector QR, which is 1, 5, 7, and you're going to get 5 -4 and then 4. So position vector of point S is 5 -5, 4, 4, or the coordinates you write it horizontally. Okay, the last example, here we have to prove that the diagonals of the cuboid OE and so the diagonals OE and BG bisect each other. So remember, you've got here, this is an important point to make. If you've got 3 vectors that are non-coplanar, that means they are not belonging on the same plane, then you can compare their coefficients on both sides of an equation. So if you've got combination of these and you know that that combination is equal to a vector or another combination, then you can compare their x components, so your I parts, j components and k components, so y and z components, and they should be equal to each other if it's an equation. Okay, so we're going to prove that these this point here is bang on in the middle of those 2 diagonals, so I need to prove that they bisect each other. So this length is equal to that length, is equal to that length. So the key thing here is to make sure that you label that point, maybe M, where they meet, or the midpoint if you like, and we are going to express a vector, so position vector of point M, so OM, in two different ways. So one that you're going to get there using this diagonal, and one using this diagonal, making sure that we use the fact that the side, perpendicular sides, can be expressed in terms of vectors A, B, and C. Okay, so first of all, let's write it down, OM along the diagonal OE. So this is equal to half. We don't know that, okay, because we're going to prove it. So we're going to put K OE. So imagine that OM is a part of OE. We don't really know exactly how long. Okay, so that's the first way of doing it. And then, so we're going to find that using this diagonal. Okay, and then we're going to get from O to M using the other diagonal. Okay, so now I need to find a way of expressing OE in terms of our other vectors that we know. So imagine we only know the little letters. So to get from O to E, let's just imagine going from O to E. Maybe we could use, let's say we can go along this side, so A, then we can go along this side, so we're going to go along C, and then we're going to go along this side, which is B, because all of these are B's, and that's C. So that's going to be K, lots of A, add C, add B. That's it, that's the first one done. Okay, let's do the second one. So the other way of getting from O to M, let's use the other diagonal. Okay, so to get from O to M, we can go along OB. So it's along vector, let's put it OB, and then add, let's put it P, lots of BG. So P lots of BG. Okay, so OB is vector B, and then you've got BG. So BG, how do I get from B to G? So to get from B to G, I can actually use these sides here. So I could go along BF. I'll put it on the top here because I haven't wrote it before. I can go along vector FE, and then along EG. So what are these vectors in terms of our little letters? So BF is our vector C, so it's C. FE is the same as this vector, which is A. And EG is actually going in opposite direction to B, so it's minus B. So it's B plus PC plus PA minus PB. And that's our OM, using a different way of approaching these. Now I know that OM from the first equation must be the same as OM from the second equation. So this is equal to K A plus C plus B equals, let's gather these together. So it's, well, it's actually, let's copy that and then tidy it up. So there you go. So anything on the left hand side must be equal to the right hand side. So let's just expand it and put them in order you've got k lots of A, k lots of C, k lots of B. Here we've got p lots of A, then we've got, how many B's have we got? Well, we've got 1 minus p, factorize these, and then you've got p lots of C. So for these to be equal, the number of A's on that side must be equal to the number of A's on that side. So it's k is equal to p. That's by comparing the number of A's. If you compare the number of B's, you've got KB's and PC's. You get the same. So that's not really much. And then comparing the C's, you've got KC's on that side, and you've got 1 minus P on that side. So taking up two of these equations, you can solve them simultaneously. So if you replace that P with K, you get K is equal to 1 minus K. So putting the two K's together, 2K is equal to 1. That gives you the value of K must be equal to a half. And the value of P must also be equal to a half. And what does it show me? It shows us that OM must be equal to a half of OE. And also OM from this is equal to OB B plus a half BG. So you go along B and you go to half of BG, so they bisect each other. Proven. Okay, so the key thing to remember is when you have improves like this, the same way you did it last year, you try to, when you prove that something bisects each other or splits itself in a given ratio, try and express the way of getting to that position in two different ways. There you go. So now you can go on to exercise 12B, I think. We'll see.